Hi folks, my name's Andrew. I'm going to be talking about the missing step, making data-oriented design faster, sometimes really, really, really faster. To do this, I'm going to use some problem-solving techniques from an eminent mathematician, George Polya, who coincidentally used to teach John von Neumann maths, if you can imagine. The central example in this talk is going to be a leave one out regression run. We used to do this in a machine learning quant fund. The takeout is 14,000 seconds, initial or reference run, 18 milliseconds, final run. It's not about actually running a million times faster, or even this particular application. It's how we get there, because how we get there is transferable. We're going to start off with classic data-oriented design. In 2014, Mike Acton, wearing a lovely shirt like this, it seems to be compulsory to talk like this, explained to us that if we understand the data, we can understand the problem. The guy that I'm introducing to help us out, George Polya, introduces a kind of structured problem-solving approach and gives us a how-to, detailed techniques. Don't just understand the data, do this. He gives us a process. First of all, we've got to understand the problem. Then we formulate a plan, and it's not just a silly Gantt chart. And then we execute the plan and we reflect. His main weapons in problem-solving are heuristics, such as decomposition, reasoning by analogy, and he has some other interesting side parts to his techniques. Having taught his approaches to problem solving to his students, he's watched them fail to solve problems, and he understands why that is, and so I'll explain why we fail to solve problems. And another good thing is, that he mentions is, when you're solving a problem, it isn't kind of a binary thing. We aren't reinforcement learners. There's start, I haven't solved the problem. Flash of light, I have solved the problem. There's signs along the way when you're actually making progress. And it's quite nice to have some of those so that you recognize that you're progressing rather than going around in a circle. So I hope your takeaway from this is new places to attack performance problems and concrete tools and checklists to do it, and an interest in getting a copy of Polya's work and trying to interpret that for yourself in your own circumstances. But first, let's just have a quick recap of data-oriented design. There's going to be an excellent talk on that as a keynote speech, so it's not wanting to overlap with that. Mike Acton, red shirt. Programs just transform data from one thing to another. Understand the problem to understand the data. Understand the data by understand the data to understand the problem. Understand the cost to understand the problem. Understand the hardware to understand the cost to understand the problem. Code is data. There's kind of nothing wrong with that. Context, this is in capitals. The more you have, the better you can make a solution. This is really, really important. I'm going to show how not quite keeping the context wide open causes us to get poor results. Software is a real thing running on real hardware. Well, I guess so. Reason must prevail, evidence. And finally, don't solve problems you don't have. I haven't given this capitalization because I don't believe it. Because today we're going to solve problems we don't have, to solve problems that we can't solve. Fair enough. Other sources of information on data-oriented design. There's a nice book by Richard Fabian, and he mentions the power of ordered data, which seems to have got lost in the mix somewhere. And it's very, very important if you've got ordered data because you can use better algorithms and many other things as well. And there's a nice talk on the software, a nice article in Overload, February 2022, on the software engineering aspects of data-oriented design. So there's plenty of stuff to go and look at, just to bulk up. But that's not what we're really doing here. In the real world, the real design problem, well, it's a lot worse, isn't it? It's a lot more complicated. It's so highly dimensional. We've got decomposition choices, algorithm choices, compile time offloading. If I can offload this, then it's going to be better, isn't it? What about the spatial layout of the data so that we keep cache coherency? It's starting to get a bit busy in the head, isn't it? And now we've laid it out, all we can do execute and have the temporal coherency. Yeah, it's starting to get really tough. How about, are we executing our code optimally? Would there be a better way of executing it? Now it's starting to get really, really busy. And of course, we want to use SIMD if that's available to us. Why go for something that's only going to run at a maximum of 10% when we can go at 100%, having 8 doubles processed simultaneously, if it will scale? Oh, caching and execution ordering. How are we going to make sure our caches are sorted out so that we can reuse the intermediate results? How are we going to stop ourselves from having to look up things in random unsorted data? What are we going to do there? Oh, and high-dimensional data too. It can get really, really awkward. And so that's what we tend to focus on, because there's enough there to put people very busy. But it isn't everything. We've got to consider these factors in the context of the problem domain. It's very, very easy to bury our heads and say, I've sorted out the data, the cache locality, it's great. But what if you've not really understood the problem domain? What if there's huge wins by understanding the issues in the problem domain? It's very easy just to bury your head and say, oh, I've got cache locality, I'm great. I've got SIMD, I'm great. But having a broader context for your problem understanding. So I'm claiming that there's a kind of a logical algorithmic bit to the design problem. There's the spatial temporal ordering layout sequencing stuff that we do. And then there's this idiosyncratic stuff. What is a performance solution in one domain? It is entirely due to that problem domain. We might have side information and constraints that we can exploit to do something that's even better because we understand the problem better. We've dug into it. And there might be patterns in the data. What if the physics of the data world had recurring patterns and we knew that, and we could sort our data so that we'd access lookups so that the lookups were always hot? So what I'm suggesting here is the missing step is a way of working all these aspects in a sort of heuristic, disciplined manner with at least some sort of plan. And the tools that I'm proposing that we use are Polya's problem-solving approach. He's got a life cycle, as I mentioned before, and heuristic. And when we were doing work, we were asking questions. Because to get good answers, you've got to have good questions. And Socrates had a set of nice types of questions. It's just good to look at that checklist and see, what if I asked a question that was probing beliefs or something in this particular part of the work that we're doing? So let's have a look at solving the design problem according to George Polya. George Polya, as I mentioned, was an eminent mathematician. And he wrote this wonderful book. I read this book as a teenager and devoured it and loved it and have been using tricks from it in problem-solving challenges I've had. There is a QR code there for people that might want to have a quick look at the book. Take the book. Get your cameras out, guys. It's a really good book. Oh, sorry, guys. If you want to... So, yes, his work was appreciated by many people. Thank you. Yeah, his work's been appreciated by many people, and many eminent mathematicians have made forewords in various editions of his book. Marvin Minsky, everyone should know the work of George Polya on how to solve problems. So, and I think he sold about 1 million copies of the book. In a nutshell, his approach says, understand the problem, devise a plan to solve the problem, execute your plan, and reflect. These are exact words. I've not tried to translate them to a design solution, because I think if you see the raw words and you translate them in your own mind to your own problem, you kind of get an interesting variation of what you're looking for and what the question's actually asking, and it kind of customizes itself to you. So what's the unknown? The unknown is the solution to this problem that we're working on. What's the data? Excuse me, that's everything we know about the problem. What's the condition? That's, say, the performance requirements or memory requirements that we're trying to satisfy. These ones, the second row is hopefully not going to apply to us. Is it possible to solve the problem? Does it have a solution? Well, we hope so. Moving on, can we separate various parts of the things that we're trying to satisfy and write them down? Sometimes it's really, really good if we can dig back into the statement of the problem that we're working on and look for little chinks in the armor, ways of rephrasing that problem, they can give you different ways of attacking it. And the next part is draw a picture. Most of us are stuck to our keyboards, staring at the screen. We don't use our hands to draw pictures and engage like that. But I like doing that, and I'm going to use social proof about why drawing a picture is good and why you should do it when you're stuck. So James Clerk Maxwell, Richard P. Feynman, Da Vinci, he's actually quite good at drawing pictures. And it'd be good to top it off with two other guys that you may have heard of, Isaac Newton and Einstein. These guys kind of drew pictures when they were solving problems. What do they know? Right. Yeah, exactly. So the first part is devise a plan. What's the connection between the unknown and the data? What's the connection between my final solution to this problem and what I know? Have you seen the problem before? Do I know something related or quite close to it? Can I restate the problem so I understand it? Do I understand all the terms? Look closely at this thing that I'm trying to build. Has somebody else done something similar? Can I copy what they've done? Remember this circular buffer that people were using? If you're not in the fortunate position of doing something very similar to what you've been doing, then it's going to get tricky. And you may not have a clue what you're going to do. You're stuck. This doesn't faze our George. He says, well, just find a problem that you can solve. It's kind of simple, isn't it? By finding a problem that you can solve, you're getting a feel for the solution space. And so what he advises is create an auxiliary problem that's very, very similar to yours, and that by solving that, you'll learn something. And we're going to do that to solve some interesting real-world problems that some very, very capable people from the best universities with lots of experience might have been a little bit stuck on, and I might help them out. So they are very real. There's no point reporting on something that's made up. This is very real. It does work. So creating a useful auxiliary problem is very, very important. This bit, do you use all the data, and have you taken all the essential notions involved in the problem into account? This is really quite important. In a maths exam, if you've not used all the data, you know you're solving it wrong. Real problems aren't maths exams. But if you're not using all the useful facts, you're not going to be able to get some extra constraint to put on your solution to make it better. And now for the heuristics, reasoning by analogy, decomposition and recombination. This isn't problem decomposition, break it into parts and solve bits. This is break it down into tiny bits and then reassemble those tiny bits to mean something slightly different. Generalization and specialization. Can we solve a more general version of the problem? Is it easier to solve a more general one? Or specialization, exactly the opposite. If I fix things, can I make a version of the problem that I know I can solve when I've tied some things down? Working backwards. If I know that this is the answer to the problem, what was it, the bit that happened before that? And then the most common bit is auxiliary elements, constructions, diagrams, notations, intermediate goals. And finally, we have reduction, where we can map the problem that we have, that we don't think we've got a solution to a new domain, where we know that we've got a solution, solve it in the other domain and map it back. This is all a bit abstract, but we're going to do a real example shortly. Carry out the plan. Okay, we're just going to do the work. Be diligent, make sure that the new improved function that's running faster still gives the correct results. It's kind of important, that bit. And finally, once we've got a solution, I think we've got to check the results. Is the solution that we've got, is it just so obvious and we can't see how we wouldn't have got it right from the start? And have we solved the problem the most efficient way? If we face this thing again, what's a better way of doing it? And finally, the answer to this particular problem that we've got, could we reuse it somewhere else? Diagnosis. So from studying his students fail at problems, the principal reason for failing was an incomplete understanding of the problem, lack of concentration on understanding the problem when they first started. Now that sounds like Mike Acton to me, understanding the problem. The next problem was a planning failure. I'm not saying anything about Agile here, just diving straight in, having a go. No idea what they're looking for, no idea where they're going, and then they don't get anywhere. And then the other guys sitting there meditating, waiting for the big idea. It doesn't come, they're just sitting there waiting. But there are things that you can do in terms of auxiliary problems that will improve your understanding. And finally, after having avoided all those things, they screw it up by being a bit careless. Solving hard problems isn't just a methodology or techniques or technology. It's unfortunately involves a lot of our own mental state. We have to have a certain degree of persistence and a positive mindset, maybe a growth mindset. If we don't believe we can solve a problem, we're going to give up a bit too easy. And then we end up with a sort of self-defeating attitude. Keeping notes on what you did and having a good approach to asking questions will be beneficial. Socrates developed his questioning approach. Unfortunately, he asked too many of the wrong questions and died early because of it. But, but apart from those, I think maybe that's understanding the context bit. Maybe you didn't get that. There's clarification, probing for evidence, alternative views, implications, and meta-level questions. If you're in a sort of a questioning phase and you want to find something out, just think about this as a checklist and see if you can ask yourself some questions of this style relating to what you're doing. They might give you an insight. Okay, right, where the rubber hits the road. This is a problem I actually faced in finance. A troublesome function, which is very, very expensive in what's called a moment matching pricing algorithm, where we're transforming the pricing of an exotic instrument to a Black-Scholes simple instrument. That's irrelevant. From a technical point of view, we had a great big square matrix, a bit like a correlation matrix, where there might be some symmetry across the diagonals. And every element had to be filled by some horrible, horrible, expensive function. The axes on the matrix were positively increasing time axes, corresponding to futures expiry dates. But really, this matrix, time axis, cell, expensive function, and summing over all the elements of the matrix. So it's obviously going to be n squared. So the initial code looks something a bit like this. We have a double nested loop and call f_impl, which takes the three arguments, the little t, the time that we're looking at, and the index of the cell on the array that we're looking at. We add them all up. However, inside the expensive function, f_impl, it looks like this, the bottom function, where actually they're just taking the minimum of these three times. So when I looked at this, what I was thinking is maybe there's some strategy where we can work with this possible reflective symmetry across the diagonal of this matrix and maybe cut it down in half. As you see, there's a lot in matrix code. But this min thing, I'd never seen it before. So how are we going to solve this? How are we going to see if there's any way in which we can avoid calculating so much? Well, we're going to simplify it and create an auxiliary problem and have an investigate. And then I like to draw pictures, so I'm going to draw a picture. It doesn't sound very hard. And honestly, the guys that were working on this, very, very smart guys. So the first thing we're going to do is we're going to drop the little t, and we're just going to look at a problem where we just have a big square matrix with equal values, integers across the top and the bottom, this minimum condition. Okay, simplified. The next thing we're going to do is we're going to turn these from dates just to integers because this min thing is just going to behave the same anyway. And finally, this expensive unknown finance function that's called for every cell, we're just going to return the input value. Why are we doing that? We're doing that because what we're looking for is when this function is called with the same input value, if we cached it, then we're going to know where we're doing the caching. So let's draw the picture. Plot the matrix. So here's our example 7 by 7 matrix. And we draw this min stuff inside. And then we add the magic pattern recognition. And when I saw this, it was awesome. Because that means we've got 7 independent regions, not n squared. Just drawing the picture. I mean, I haven't solved the whole problem yet. But it was really, really good. So the next bit to this is just polishing this thing off. So we're going to take it back to where we came in and add this little t back in. Oh, yes, the other thing. We actually know how big these regions are as well. So what we can do is we can evaluate this function and then multiply it by the size of the regions. That's it. Now let's bring in the little t. If the little t argument is less than the first element, then it's going to win out on all min comparisons. So here we have it. We just call the function once and multiply by n squared. Yes! If little t is greater than the last element, well, that's just dropping an order from it, which is a fantastic result. And if it's somewhere in the middle, then we get this kind of hybrid. So just by simplifying the problem, drawing a picture, we kind of got a really, really big win. I mean, who doesn't want 40 times performance improvement? So what I've done as well on this, oh yes, of course, with those kinds of features, I was thinking also using others which had hourly rather than monthly exercise. And so let's just make this n squared problem 700 times worse on the axis, so 700 squared times worse. So just simplifying the problem, drawing a picture, huge win. This is what the auxiliary thing looks like when we implement it. We just call the f-impl and multiply it by the size of the region. When we've added the special case, I don't know if you can see this. This is vibe coded. I vibe coded it because I wanted to run it on Godbolt quickly. Here's a QR for it. And when we run it on real code, the speedups are 263 for the small t, 61 times faster for somewhere in the middle, and then the worst case, it's only 40 times faster, just for drawing a picture. Awesome. So that's the first example. It didn't take, well, actually in real life it was much slower and I was more bumbling, but yeah, it was a very, very nice result. We'll move on to the second example now, leave one out regression. This comes from machine learning. I was part of a quant fund in a well-known British bank, and we were using machine learning to try and predict which way the market went so that we could make forecasts, and from those forecasts make bets, work out what bets we wanted to make and blend them into a portfolio and then invest the money. Yeah, it's just about getting rich, really. Now, these models, they have various predictive factors, and we wanted to search the whole space for which predictive factors would be good. With leave one out regression, what we do is we do a fit over the whole data set apart from one point. Then we apply that fit to forecast the value at the point that we haven't included. And we do that for all the points in the data set. So we're doing a lot of fitting and forecasting. The difference between the forecast and the actual was stored as what we call residuals and ordered. And to make it more robust, because we were after robust forecasters to put into the model, we would estimate it by what we call interquantile range. So we'd have this distribution, and we'd work out the sort of bottom 5% to top 5%. And if the forecasts were in a narrow range and stable, then they're quite good things to put into your predictive model. But we ran through sort of millions of these things. So millions of possible things that might be predictive, and fits on fits on fits, try and get the best ones. It did take a long time. In fact, on my first day, two of my colleagues were walking out. They'd been trying to do a back test over the whole weekend, running it manually. They looked dreadful. So obviously speeding this sort of regression stuff up has social benefits. Fitting n-1 data points inside a loop, it's a kind of order n squared thing. We also wanted to make sure our fits were robust, so we did a thing called regularization, and we added an extra term to penalize the slope parameters. So let's get on to what Polya thinks we should do. Understand the problem, ask questions about the data and the size. There's lots of it, it's very big, and we've got to process all of it. Performance requirements, we want our staff to be able to go home at weekends. Accuracy requirements, never quite figured this one out. We want our stuff to run with the lowest accuracy possible, so it's running as fast and efficient as possible, but not give us bad results. I didn't solve that one either. Have I done linear regression before? Yes, lots of times. Have I done this kind of leave one out stuff? I hadn't worked with econometric guys before, so no. We were using a well-known analytics library providers versions. But for us, we want to look into this thing and see why is this thing slow. So I'm just going to breeze through some standard regression maths. It might be better just looking on Wikipedia if you're terribly interested in this. When you're looking for predictive factors, it's usually best just to go for the simplest thing. And so we went for a very simple straight line. We had, with this and the next layer, the objective function, we want to try and find the slope and the intercept B1 and B0, which minimizes the square area, which when you have a normal distribution gives you the most likely values of those parameters. We didn't believe that was the case, or our econometrics researcher, professor guy, didn't, and went with a fairly standard technique of having an extra term on here which penalizes the slope beta 1. Now down to the regression stuff. This is classic stuff. We have a column of our x values, and additionally a column of 1s, and a column of our y values, which was what we observed, and a very small column of our parameters that we're fitting. And we have a little square matrix with the lambda on the bottom right for penalizing the slope. Moving on to the classic regression, linear regression formulation. In the bottom one, we've got the beta, or the fit, is equal to xtx plus our ridge regressions term inverted multiplied by xty. And inside here, we have these matrix sums. So basically, we're just creating little small matrices. And the bits that look troublesome are when I've got these sums over all the x values, or all of the x squared values, or the sum of xy's over the whole data set. Because we're doing a sum over n objects, rather than just being a scalar. We can rework this, and we'll end up with this formula for the slope and the intercept. So what can we do to make this quicker? So the approach is we're going to understand the problem first, identify what are the slow bits. We've seen all these sums over x's and x squareds. It's not a bad bet. Then we're going to have a look at an auxiliary problem. We're going to draw some pictures and then possibly generate another solution. So let's pick the XTX matrix. It doesn't really matter in here. We can look at x squared or sum over xi. These things are going to be slow because they're summing over the whole data set. So what can we do? Well, let's also remember that we're also computing these things for every time we're doing a refit. And it's this XTX term which introduces this order n, as was the XTY term. These are the things that bring this big length dependence to us. So let's just consider the slow bit repeated n times, this matrix. How are we going to make this faster? Well, we have a sum over the given x values. How would we make that faster? Well, we're going to put it in a vector, aren't we? It's going to be contiguous. And, well, I suppose we could use unsequenced reduce or transform reduce for the x squared. And we could scale it with threads and SIMD. And that's in the inner loop. It's going to go faster. We're doing a really good job, aren't we? Yes. No. It looks so innocent. And this is the point where we've actually just about screwed up our chances of doing something really good. If only it was like dereferencing a null pointer. What have we done wrong? Nothing. We've made it go 10 times faster. We're heroes. Everyone will love us. Well, not really. Well, it depends. They might not know that you screwed up. We've applied an answer that we know to a problem that we recognize. It's good. But what we've done is we've not appreciated the context of the problem fully. We're only looking at the inner loop. And this completely constrains the kind of solution that we can get. I mean, 10 times faster is good, but 1,000,000 times faster, well, that's 100,000 times better, isn't it? So let's see what we can do. We want to expand the scope. Not just the inner loop, we want to look at the whole thing. So we're going to create another small problem. So let's pick an element of this XTX. I just picked summing over x rather than x squared or summing over 1. I thought this would be informative. It doesn't really matter. We just pick one and go with it and see where it takes us. How does this summation vary for the n minus 1 times we're going to be computing it? It's a good question. I think we should have this as an auxiliary problem and draw a picture. And here's a picture. The rows are all the data and the sums that we're doing to leave one out. Now, there's an awful lot of repetition in there. And in terms of times of progress, we're seeing the problem differently. We've broadened the context in which we're exploring the problem. And all this redundancy, this repetition, if only we can exploit this, it's going to be really good. I didn't think it was going to go quite so much better, but, but yeah. So let's get on. Let's, instead of having this big square table, let's just reduce it to 2 rows of the top thing. And a simple question, can we reuse the sum from the first leave one out to calculate the second row? And this is when this sort of bittersweet feeling really thick occurs. Yes, we can. The sum of leave one out row 1 is the sum of leave one out row 0 plus x0 that we'd left out minus x1. And the sum of leave one out row 2 is sum of leave one out row 0 plus x0 minus x2. So, yeah, there's something fishy going on here, something I didn't quite get. But the sum of leave one out 0 plus x0, that's just the sum of all the elements. And this becomes a candidate for an auxiliary variable that we've kind of found pretty useful. So each leave one out sum is just a sum over everything minus the thing that we're leaving out. So I don't have to sum over everything and miss one out. I can sum over everything once and then take one out. Is that it? Well, it kind of is. Does this generalization apply to all the sums? Yep. So what we've gone from is we've gone from an n squared to something that's like 2n operations. And how have we done that? We've expanded the context. We've not done that in a loop, instant hero stuff. We've worked the problem and understood that this magic variable that appeared and made us feel stupid when we saw it, the sum of the leave one out sum is the sum of everything, take away the thing we're leaving out. So our new algorithm is just going to be summing over these quantities, summing over x, summing over x squared, summing over xy, and summing over y. This is going to run really fast. And we're going to write it in a vectorized form. A couple of years back, I gave a talk on writing fast code using generic lambdas instantiated with SIMD types. And so I've kind of got my own versions of non-standard transform and reduce. And I'm going to do an implementation of this a little later. So the new algorithm, compute the sx, sx squared, sy, and sxy, and generate the leave one outs by just subtracting the values. On reflection, can we generalize this trick? You can. So if you've got a reduction over a big set and you want to compute perturbed versions of that set, just try, and there's an inverse operation to the thing that you're using your reduction. It's a lot quicker just to generate the leave one out version. I think also we found there are certain benefits for expanding the context and using the auxiliary problem approach, and also by working problems by hand where we get this feel for what's going on. If you'd done a postdoc or postgrad course in matrix computations and you'd got this book, I got this book after I'd done this, then you would have possibly found some matrix update method which would help you. But we've never always read the books that we needed to know everything from when we face problems. So let's move on to the technical aspect of implementing it. I have a library called dr3, dr cubed. It lays vectors out contiguously in memory. It's got a memory pool, and we can apply vectorized math operations across the vectors. It's available at my GitHub repo here. And we can use basically transform reduce. And by using auto, we can switch around the implementation for the SIMD operations. The data type's called vecx, memory managed, supports math functions, contiguous aligned padded, and we can change easily between scalar and vectorized instructions. It just makes it very easy to translate a scalar bit of code into something that's vectorized. And here's a picture of our memory pool. So this is the function, these are the functions that we want to implement. Can we see this? So the first three are just saying out the lambdas, so multiply, square, sum. Then the next four rows, compute the sum over x and y, transform reduce to get the sum squared and the sum of xy. So these are all vectorized. Then we generate the leave one out matrices by taking these scalar values, sx and xy, and subtracting the input vector. Now that will generate a vector of the leave one out values. And we're now ready to move on to the final implementation down at the bottom here. If we look at denominator, they share a common denominator. So we can just calculate that. It just maps straight to the equation where sz is really n, or n minus 1 as you want to call it. Calculate the numerator for beta 0, basically transcribing the equation, And it just handles this with element-wise operations. And we get the beta 0 and beta 1 calculated, all of them. And when we run it, it runs in 18 milliseconds, doing all of it. Now that seemed kind of impossible at the start. We're doing 1 million fits on a 1 million element data set. And now the behind the curtain, you can see it's doing something a little smarter. But still, you know, if you've got something doing a billion operations a second, doing a couple of, well, 20 or so million operations is going to finish in about 20 milliseconds. So it's perfectly reasonable. It just seems impossible because we didn't really understand the depth of the problem. And now for the last heuristic, can we make these sums more accurate? Because we're summing over a big set. This is a chance to think about a heuristic mini of working backwards. So how can we make sums more accurate? If you wanted to add two numbers together, we're going to get the best results when they're of the same order of magnitude. So let's say the numbers all have the same value. Say we've got 128 of these numbers, and we were adding them together. What's the last sum that makes this sum most accurate? The last sum is going to be adding two partial sums of the same size. To do that, we're going to be adding two halves. We're working backwards. So if I had a set of 128 doubles, I'd have the sum of 64 doubles on one side and the sum of 64 doubles on the other. And my last operation would just be to add these two sums together. It doesn't matter how I added the two lots of 64 sums, but my last operation is adding two numbers together which are of the same size. To get the sums of the 64s, well, same again. So we go from halves to quarters to pairs. And this is a balanced summation. So this is not what we have in the library for adding numbers. In fact, we've got exactly the opposite. So this is a nice little picture of it. One big set split into halves, into quarters, and going down to pairs. So does this work? So we'll do a little experiment. We're going to get 10 billion 0 to 1 numbers and add them up using a for loop, std accumulate, std reduce, pairwise reduce, and also a reference error correcting summation technique by Khan. So first of all, let's just do the sums. It's quite reassuring that your for loop, std accumulate, and reduce are giving the same answer, isn't it? If you look at the disassembly, well, actually, they're all doing the same thing. It's not actually three independent flight computers. It's just doing the same thing. The pairwise sum and the Khan sum are also agreeing. They've got a different answer. So what do you think is going to happen when I shuffle the data around and do the summation again? And again, and again. The pairwise summation actually, I think the last digit on the last column for the pairwise is it's one unit off. The Khan stays constant. And we get all sorts of stuff from accumulate and reduce. So this is me pitching, because I think we should have pairwise reduce in the standard. So how are we going to change our code to be more accurate? Well, we've got reduce and transform reduce, and if we had pairwise reduce and pairwise transform reduce, our sums would be more accurate. And that brings us to the end of the talk, but there are some takeaways. Design problems are very, very highly dimensional, and we shouldn't run away from looking into the problem domain to search for angles that we can work. if you use a Polya approach and use some of his heuristics, finding a simpler version of the problem and working that can be very informative. You could sit at your desk stuck for an afternoon, achieving nothing. Or you could find something very simple that's quite close to what you're working on, and you'll have a good feel for what works all around that problem area. Be very careful about our inner loop failure here. The hero programmer was going to get a 10-bagger, and he's just really lucky that his boss didn't know he should have been pulling a 1,000,000-bagger. So don't zero in your context. And for me, I like drawing pictures. I find that when I'm working problems and I'm drawing pictures, I actually draw the pictures wrong because I don't understand the problem. It's quite... When I've got the problem solved, I do understand the problem, and the pictures are a lot better. But solving an ancillary problem and drawing pictures is something that's... It's very, very unlikely to be wasted time. And I'll close with Polya's words. If you cannot solve the proposed problem, try to solve first some related problem. He didn't know about AI, so human superiority lies in bit was from the 80s. Going around the obstacle that can't be overcome directly in devising some suitable auxiliary problem when the original one appears insoluble. So when you're stuck, don't stay stuck. Find some problem that you can work that's going to give you some information. And final thoughts. How do you think it feels when you actually get a 40-fold or a 100-fold or a 1,000,000-fold speed up? Awesome. Yeah, no, honestly, and I'm hoping that you guys are going to try some of this stuff out, and I want you to go get the yes feeling, because it's really, really good. And if you try this stuff out and it works for you, please mail me and tell me, it'll make my day. Thanks very much, guys.
I actually have two questions.
Yeah.
First, have you considered fitting some sort of Chebyshev polynomial to avoid computing these expensive functions and get further speed up? Because then you can see indeed evaluation of these functions. And the second is, you showed how to increase the accuracy of the sum, but then you subtract one element, you add another one. Now you have a problem here because you have a big sum, big magnitude, and suddenly it is small. So how do you recover the accuracy in that case for your algorithm?
When I got the big speed up, I wasn't too worried. The reason for the... Chebyshev. Have I thought about using Chebyshev? Not until you mentioned it. But we can use this approach with fitting for linear fits. I don't know how it would work with nonlinear fits. Maybe there's some other trick that we might be able to use. Managing error when we do these sums is something you want to work with your data set. So you need to look at your own data and see how the error propagation is working. The standard library, this just adding perpetually one number to a bigger number that's ever growing is not good. Pairwise is better because all you're doing is changing the sequence. Yeah. With the error correcting cons, you can pass in I did a little talk at ACCU and showed that you can pass in a lambda, which is also got a static bit, which has a kind of a memory. And you might not want to do that because it might not work too well in when your execution context is using multiple threads. But yes, getting an accurate solution does require more work. And pairwise is the simplest, lowest hanging fruit I can see.
You know, I totally agree with that. The thing is, at the last step, when you evaluate your formula, you have the sum of the elements, which is big. Now you subtract one element, which is small, and you add another one that is small. So you're losing accuracy in the last possible step. So how do you deal with that in that case? Have you considered that?
No, I haven't, sorry.
Okay.
But I will now. Thank you.
Thank you.
Hi, great talk.
Hi, thank you.
Yeah, I got a couple things for you. First, to follow on these summations, one of the last result you showed that the results weren't deterministic, that you got different numbers each time. And so if you're looking for deterministic algorithms that also work in parallel and will give you more accuracy, there are reproducible floating point summation algorithms that you could use. And they also work nicely in parallel. You mentioned, you might know about those because you talked about passing in a lambda with some state.
Yeah.
So those algorithms have a wide accumulator and they accumulate things on each thread. So there are ways to solve that problem really thoroughly with a giant hammer, solve that giant problem.
I wonder, have you got any good references to share with the audience, Mark?
Yes, so UC Berkeley has a library called reproblas.
Oh, right, yes.
That's a good one to start with. And there are
This is the bin summation stuff.
Exactly, yeah. And I think Professor Khan would prefer compensated summation.
Yes.
But nobody calls it that, so he lost that fight, I think.
And there's a good reference by Mr. Hyam as well, isn't there?
Yeah, that book.
The numerical accuracy and stability, which can also be found on the internet.
But I wanted to ask one more thing. You showed some pictures that Newton and Einstein drew. Could you explain what those are? Do you know?
I have no idea. I'm sorry.
Oh, that's okay. Yeah, just curious. Thank you.
Thank you.
Hi, thank you so much for the talk. It was very good. One question that I had that maybe the runtime is quite fast, so not relevant unless you move to bigger data, but did you consider trying to run this code on a GPU? Because it looked like it would be very easy.
Yeah, well, it was when I was doing this about 15 years ago. So we were overwhelmed. So it was, do we try and use stuff on the grid? Do we try and use GPU? I wanted to use GPU. Everyone wanted to use GPU in 2009. I didn't use SIMD either in then. But then we didn't even have AVX2. But yes, you can see how working the problem to get this kind of speed up by just rephrasing it and putting that on something, it will give you a big multiplier, but then you put that with a big scale up on a GPU. This stuff is fantastic, actually. I haven't thought about doing it on a GPU recently. I have a 4090 at home waiting. But thank you.
Thank you.
That's it. Well, thank you very much, everybody.